Okay, so in this video we are going to study some properties of quantum Fourier transform that make them useful in algorithms. So let's remember what the quantum Fourier transform is. It's an n by n matrix. It's a n by n unitary matrix, which is expressed in terms of the nth root of unity omega. So here omega is e to the 2 pi I over n. It's a primitive nth root of unity, and basically the matrix has its jkth entry omega to the jk. Let's see. So there are two very interesting properties of this quantum Fourier transform. So so let's say that this was our quantum Fourier transform matrix, 1 omega, omega to the n minus 1, 1 omega to the n minus 1. Okay, and let's say we applied it to this state, and we got as output right. So we are assuming, so what we are saying is that f sub n applied to this state summation over j alpha j j is equal to summation over k beta sub k k. Right? That's the result of applying this transform to this. Okay, so now let's consider what happens if we apply the same transformation, the quantum Fourier transform. So we apply this same matrix. Okay, so we apply it to a shifted version of the. So what we are going to do is we are going to shift our input superposition, and so we shift it cyclically. So let's say we shift it by one position, but then, as you'll see, the same principle will apply no matter how much if we shift by many positions. So let's shift everything down by one position. So you have alpha naught moves down to the second position, alpha 1, alpha n minus 2, and then alpha n minus 1 gets knocked out and moved to the top position. And now we want to understand what's the quantum Fourier transform. Well, the answer is particularly nice. So what it says is basically everything stays unchanged. Okay, so all these amplitudes on this side basically remain the same, except that they get multiplied by a phase. And what phase is it? So meaning a complex number of unit magnitude. And in fact, it's actually going to be a power of omega. So what power of omega do we have? Well, it depends upon which row we have. So this first one gets multiplied by 1, the second one by omega, the third one by omega squared, and so on up to omega to the n minus 1. Okay, now here's the important thing. The important thing is that each of these, it's not what the actual value is, it's the fact that these are all unit magnitude. So now, if we were to do a measurement at this point, what we'd see is k with probability beta sub k magnitude squared. Exactly the same as if we did the measurement up here. You see k with probability beta sub k magnitude squared. So the moral of all this is that if you start with some superposition, and if you're going to do a Fourier transform, a quantum Fourier transform, and then measure, so if you're going to do quantum Fourier sampling, then doing a cyclic shift of the input superposition doesn't change the output distribution. Okay, so now to some of you, this this property of quantum Fourier transforms might look very familiar, and the reason it looks familiar is probably because it is. So this property that when you shift the input superposition, the output superposition just gets multiplied pointwise by a phase. This is the same thing as this is the convolution multiplication property of the Fourier transform. Okay, so well, see if you can, if you do know about the convolution multiplication property, see if you can figure out why this is the case. So what are you convolving, and what is pointwise multiplication, right? So just to give you a hint, this is where you have pointwise multiplication. You're multiplying pointwise by this, by these phases, right? So really, okay, so this is what you're doing. You're multiplying the Fourier transform of something, which is the beta naught through beta n minus 1, pointwise by 1 omega omega squared omega to the n minus 1, which is the Fourier transform of something else. Okay, and so what you're getting on the left hand side, you're getting you're starting with this particular vector, and then you're convolving it with something to get this shifted vector. So that's why you're getting a convolution on the left and pointwise multiplication on the right. See if you can figure it out if you happen to know about the convolution multiplication property. Okay, so now let's prove a second very important property of the quantum Fourier transform. This property says that if you start off with a periodic function, then the quantum Fourier transform is going to map it to a periodic function. So let me say this in a little more carefully in terms of how we've been thinking about it. So let's say that our input superposition was summation alpha sub j. So j, of course, goes from 0 to m minus 1. Right? So that's our input superposition. And now we are applying the Fourier transform to this. And we get our output superposition, summation k equal to 0 to m minus 1 of beta sub k. Okay, so what's periodic here? So remember, what we are doing here is we are plotting j along this axis and alpha sub j along that axis. So what we are saying is that these amplitudes are periodic, meaning that alpha sub j plus r equal to alpha sub j. Right? That's what it means for it to be periodic with period r. So when you add r to the index, you get back the same amplitude. So we are claiming that this implies that beta must also be periodic. Okay, so what's beta? Well, so here we are plotting k along the x-axis and beta sub k along this y-axis. right? And what we're claiming is now beta must be periodic with period m over r. So beta sub k plus m over r must be equal to beta sub k. Okay, so we've already seen an extreme case of this. You know, so let's write it out over here. So suppose we apply f sub m to the uniform superposition to 1 over square root m sum of everything j equal to 0 to m minus 1 of j, right? So it's, you know, this is a superposition over everything from 0 to m minus 1. And what's the Fourier transform of this? Well, it's just 0, right? And so, well, this superposition has period r equal to 1. So here we have r equal to 1, and so m over r is equal to m. So this is a superposition with period exactly m, in the sense that this is a superposition which starts, you know, which is a delta function at 0, and then there's nothing all the way up to m minus 1, you know, which is everything we have. And then of course if we made it periodic, we'd get another delta function at m, and then nothing all the way up to 2m minus 1, and so on. But of course we are only limiting ourselves to 0 through m minus 1, so the period is exactly m, which is like saying we ended up with this delta function. Okay, so that's this, that's our second property of the quantum Fourier transform, that it treats periodic functions extremely nicely.